Hello and welcome back. I just wrapped up classes for the day and I wanted to talk a little bit about why disks are shaped and sort of designed the way they are. And that's going to set up the next couple videos where we talk about the effects of that and why disks skip when they hit the ground and why they fly the way they do with their S-curve when you throw them fast enough to give that full flight. So pretty exciting to talk about this topic because it's going to set the stage. It's going to build off of what we've already talked about and set the stage for topics that are coming up. In particular, we're going to talk about something called moment of inertia, but we're going to build up to that. So in review, I want to talk a little bit about some of the things we've already covered in past episodes. Specifically, we said that when something has mass, like this is a mass of 156 grams. Grams is a measure of the mass of an object. And there's a couple different ways you can interpret mass. It's essentially just how much stuff is in the object that you're talking about. And we talk about mass in terms of how much gravity is pulling it down. That's called the weight of an object. That's what weight is defined as. It's the attractive force between the planet Earth and your mass that makes up you. That's your weight, or the disk's mass. That's the amount of matter that makes it up. But we can also talk about mass in terms of inertia. Inertia is an object's resistance to its state of change of its motion. So recall that it takes force to cause stuff to accelerate. Accelerating is a change to its state of motion, and it takes force to make that happen. If I want to push my desk, I apply a force and it accelerates. If I push harder, it's going to accelerate more. If I push lighter, it's going to accelerate less because there's a certain amount of mass and the amount I push is related to that. So Newton's second law, F equals ma. If force goes up, acceleration goes up. If mass goes up, acceleration goes down. A consequence of that is Newton's first law. It takes a force to change an object's motion. If I put the disk on the table, on the desk here, it's not going to start moving unless I apply a force to it. If it is moving already, it takes a force to make it change. So in the absence of an outside force, objects are going to continue doing what they're doing. Objects at rest will stay at rest. Objects in motion will stay in motion unless acted upon by some outside force. In other words, the inertia of an object, which depends on how much mass it has, the inertia of an object means that it will resist any changes to its state of motion. It wants to keep doing what it's doing. If you've got a boulder rolling down a hill, you don't want to get in its way. It's got a lot of mass, and therefore it's got a lot of inertia pushing it down the hill. Spinning objects have a similar quality about them. So a spinning object wants to continue spinning exactly as it is in the same plane unless something makes it change, some outside torque. Now, I made a video about torque. So if I want to make this spin, I apply a torque to make it spin. But in order to change its axis of rotation, I also have to apply a torque to make it rotate this way. So torque is required to change the spin of an object. And in the absence of any outside torques, it doesn't want to change. Now, there was an outside torque provided by gravity there just a second ago, and you saw it caused it to, there it goes again, follow a very interesting pattern. Now, we're going to get into that when we talk about gyroscopic precession in the not too distant future. But in the absence of outside torques, it doesn't want to change. It's just going to keep spinning the way it is. That's why it's bouncing on my finger. A cool demonstration of this is a gyroscope. Here, we'll put it right on top of this box. A gyroscope is a spinning disc inside of a frame. So I'm going to give it a pull. It's spinning like crazy. I can balance it. There we go. Now, I bought this toy specifically to show some cool aspects of gyroscopic precession, and you can see it processing around there, which, again, we're going to get into later. But in order to understand why that's happening, we have to understand the concept of rotational inertia, or moment of inertia. So an object has mass, it wants to resist changes to its state of linear motion. That's just called inertia. When an object is spinning and it wants to resist changes to its state of spinning, that's called rotational inertia, also known as moment of inertia. But unlike an object that's just sitting here where I want to move it and slide it, the only thing its inertia is dependent on is its mass. A spinning object, its moment of inertia or its rotational inertia depends not just on its mass, but where that mass is located. So I made these 2 meter sticks with weights taped on the end. Now this one has the weights taped way at the end, and this one has the weights taped in the middle. You'll have to trust me a little bit, but you could try it on your own if you want. When I want to try to spin this one, it's harder to make it start, and once it starts, it's harder to make it stop. This one is really easy to make it start, and it's really easy to make it stop. This one, much more difficult. It requires more force and more torque on my part to start it and stop it as compared to the one with the masses in the middle. When the mass of an object is located near the center, the axis of rotation, then the moment of inertia, or the rotational inertia, is going to be reduced. If it's farther away from the center, it's going to be increased. This is kind of why figure skaters, they put their arms out, they put their arms in. It's also why if you're a baseball player and you're not very strong, like a little leaguer, you don't want to hold the end of the bat. You're going to choke up on the bat. You change where the axis of rotation is, so there's less mass far from that axis of rotation. In fact, for regularly shaped objects, you can calculate the moment of inertia with the equations that I'm going to put up on the screen right now. Now, notice that one of those equations is for a ring where all of the mass is located on the outside edge. If you look at a disc golf disc, where's most of the mass? Is it this thin little tiny flight plate? No, it's the thicker, wider, more massive rim. As opposed to something like this. If the disc was solid, where the mass is evenly distributed, more of the mass is close to the middle where it's going to rotate when it spins. So the moment of inertia for a disc like this that's solid is going to be smaller than the moment of inertia where the mass is located farther away, like one of my disc golf discs. So even if they had the same amount of total mass, where the mass is located is important. So we're going to do a little bit of an experiment here together. I've got 2 circular objects. I weighed them beforehand. They have the exact same mass. They are identical in their weight, so they're identical in their mass here on the planet Earth. I'm going to roll them down a hill. Which one do you think is going to get to the bottom first? So I'm going to give you a second to think about it. All right, so you made your guess. It's a race. Is it going to be the one that's solid and evenly distributed, or is it going to be the one that has all of the mass located on the outside edge? Let's give it a try. Here we go. The race is on. In 3, 2, 1, go. All right. Definitely, this one got there first. Why? Well, they have the same mass, which means we have the same amount of force causing them to accelerate, but this one has a bigger moment of inertia. The mass is farther from the middle. It's all concentrated on the outside rim. There's no mass in the middle here where it's rotating about. So the bigger moment of inertia means it's more resistant to a change in its state of rotation. It is harder to make this one rotate than it is to make this one rotate. Why do we make discs the way we do? We put all of the mass, the majority of the mass, not all of it, but we put the majority of the mass along the outside rim, increasing the moment of inertia, giving it more resistance to a change of its state of rotation, which makes it fly more stably through the air. Now, the effects of that on flight and on skipping when it hits the ground, we're going to cover that in a future video. Thanks for watching.